Now, in our last lesson, well, the last video we talked about symbols. Now, in the engineering, drawing and design, there are various topics which were given, which you are aware of. And of course, I said I will not be following the way they are in the next write-up. So we are deciding to start the one on the symbols and circuits. Now, in the last video, we did explain the design word standards, and also did a little bit of symbols, of which much of it will be on your part to come up with the symbols. Now, in that symbols and circuits, we have also got motor connections which will form our next topic. Now, before we do the actual motor connections, I want us to have a look at how do we get power to the industrial situation. Maybe it's an institute or it's a production. So we have got generating stations. Now here we have got various generating stations here in Kenya. And the generating stations, there are various types. We have got hydro, we have got geothermal, we have got solar, and we have got wind. Now the hydro, Kindaruma area, Sondomiriu, geothermal, mainly around Naivasha. Solar, I think it's coming up somewhere in Turkana. And the wind, we have got it in Gong Hills. Now these ones, when you are representing a drawing like this ones here, this one will also be in symbols. Now this kind of setup here, you do it also in another subject. But remember, NEC recommends you may not be able, you may decide not to do all the subjects in one sitting. So I'm doing it for the benefits. Maybe somebody chose to do this here, decided to do engineering, drawing and design and circuit analysis, and maybe the other time do the subject dealing with all this. So it's good I introduce so that you know how the power is achieved from the generating station all the way to your workshop where you connect your motors. So all these have got symbols, which again, you can add them up in the exercise that I gave you in the last symbols video. And then the power is transmitted, is generated here, and then is being transmitted. Now, before I finish the generating stations, I think Kenya is also talking about nuclear source of energy. Of course, the question is, do we need this one? We have got hydro, geothermal, solar, wind. Now, solar, God given 12 hours in a day. I think it's an area, those who are doing a design, is an area you need to maybe concentrate on. But we are thinking also of getting nuclear power to get our more energy. We are also importing generated power from, I think it's Zimbabwe, all the way across Tanzania down into Kenya. And much of that transmission will be overhead. Again, there's a symbol for overhead transmission. And then from here, generator is about either 6 or 11 kilovolts, then stepped up to about 272, and then transmitted overhead over big pylons, and then to a substation. In our case, maybe Dandora in Nairobi. And then from there, we have got what we call primary distribution. Now this one may be 66, and then maybe a secondary distribution may be there. In this case, let's choose 11 kV. Now, of course, the voltage used here, I think, depends on the distance and the consumers you have. And then from the 11 kV, we come to what I'm calling the final substation. Many things happen here. Of course, here maybe we are linking to other stations, and there's a way they do connections here. It's not just a straight line, like from here to this area here. It's not just a single line like that one. Sometimes they have form of a ring, such that in case one of the transmission is broken, you have got another path. So there is what we call a ring in the distribution as well. So it's not as straightforward as a single line. In these substations, there are various things that are done. Voltage stepping up, voltage stepping down, and other things. And also like this ones here, they are linking several, maybe from another substation, from another station, they link here. so that in case this one is broken here, this one is available, or this one is available. And then the final substation. And then from here, is where you get the 11 kV step down to the 415 and the 240 that we have to supply for our domestic installation, which we are going to do more circuitry on this ones here for the domestic installations, the lighting circuits, the sockets and the like, and then the industrial connection for the 3-phase, whereby we connect our motors. Now, the transmissions from here to here, this one will usually be on 3 wires. So the transformers used in these substations will be delta to delta. Remember, they're stepping down or stepping up. For example, here stepping down from this value here to about 66 kV, so it's a step down transformer. So on the primary side it will be delta, on the second side it will be delta, so that we have got only 3 wires for the transmission. Now, when it comes to the final substation, we need to get our neutral. So you find in the final substation, the primary side will have a transformer which is connected in delta. And then in the secondary, this one will be connected in star. The idea of the star point is you get our earthing, and we also generate the neutral. Now this is L1, this one is L2, and this one is L3. Then we have our neutral like that. I think in electrical installation first year, you learned why we need the earthing for protective purposes. So this one is delta, and this one is star. Now, face to face, the voltage is here. From this one here, we get 415 volts. These are nominal, what we call nominal voltages. From here, from this face to this one here, we've got 415. Between this one here and that one there, we've got 415 volts. Remember, these are nominal values. And then between each phase and the neutral, the voltage is 240. So the 3-phase will go to our industrial connection, and then for the domestic, we can use the single phase so that we're able to have the 240 volts. And then in the case of our industry, these connections here goes to our what we call the bus bar chamber. like that. So from the in the final substation, now this one will be housed in a building on its own. So you find in most drawings, these ones will be, there will be a brackets like that, meaning they go outside or they go underground and they come into the other chamber where we have got our bus, and then we may be having an energy meter, how much of this energy is being supplied into these installations here. Now, in this bus bar chamber here, maybe sometimes we can have capacitors, capacitor banks for power factor correction. Remember here, we'll be connecting motors, inductors, they will introduce a lagging power factor. So sometimes in this chamber here, we may have some capacitors for power factor correction. Normally, KPLC people will be coming, when they are doing their energy reading, they also measure the power factor. Then they can tell you if it's okay, or if not, then you have to correct it. Now, correcting it is through capacitor power banks in most of the industrial installations that I've seen. But remember also, we can use synchronous motors for power factor corrections. But those ones mainly are used by power people in their substations to do their power factor corrections. Most industries, they tend to use capacitor banks. And then from here is where now we connect. Now this one here is an isolator to isolate the bus bar chamber. And then from this chamber here, if it is a factory, there are various shop floors. Then you can tap your energy from here to go to a various shop. So normally, for the outgoing, maybe to a various shop floors, of course, we use the word shop for the workshop. So this is outgoing to the shop floor. Again, it may be underground or overhead. We normally use the bracket to show what is indoor and what is outdoor. And this connection here goes through what we call fuse switches. I think you'll notice the difference between these connections here and these ones here. Now these ones here, when you operate them, you're not supposed to switch them on when there is a load connection at the other end. So from here now we go to the shop floor, coming out of the bus bar chamber. Usually this one is in a room of its own, and then outgoing. Now from here, there'll be several connections like this ones here. Maybe this one goes to one shop floor, maybe another lot goes to offices, another lot to another shop floor somewhere else. So briefly, now that's how we get our power into the workshop. Generation, transmission, primary distribution, secondary distribution. Now these ones can either be overhead or underground. The trend in towns is to go underground for obvious reasons, but in Kenya we are still on overhead, much of the transmission. Including here, sometimes when it's coming to a domestic installation, it can go underground, come up, or sometimes can be connected to the top and into the place. Similarly here, it can maybe go underground and then come up, or be joined to something like that. And then that one is this one's here, and inside also this substation here is where we have got. Now this one here is in the substation. Now this one here will be the setup in the premises of where the power is going to be used. Now in bigger industrial concerns, these final substations may be within the premises here, so that the three-phase is generated within the shop floor itself, or the industry. They bring it down there before they distribute it to the various workshops. So depending on the setup, this can maybe outside, then you just have the overheads coming in, or this one can be in the shop floor. If you've got a bigger enterprise, for example, the big institutes, you'll find that they will be having their own substation. So this one will be inside the institute or the commercial enterprise, but then this one belongs to the KPLC. Nowadays, the generating belongs to KenGen, transmission, KPLC, and then over here we have the consumer. So all this belongs to the KPLC until you reach the energy meter. Once the energy meter, the power belongs to the consumer. What he does with it is up to him. From here, the left belongs to the KPLC. So that's how we get our power to our shop floor, and then we can start our connections. We are all clear on that one. It was more or less an explanation of how we get our power to the shop floor. Now, let's look at how we go about in our motor connections. Send our power to the workshops. So, in our motor connection circuits, we'll be dealing with how do we control the motors. So, in this subtopic here, apart from the overload connections, now here we shall be dealing with IEE regulations. Will be acting as our guidelines. Of course, this will be conforming to the BS 7671. That is where the IE regulations are extracted from. Now, the things we need to note is that apart from overload protection, I think all circuits about electrical circuits, you learn them in your electrical installations, they need protection. Apart from overload protection, all motors must be controlled by an efficient switch starting or stopping, so placed as to be easily operated by the person operating the motor. A key recommendation in terms of safety. Now, for this, we use starters, and the type of starter will depend upon the size of the motor, and in any case must possess an overload device with time lag characteristics. Time lag characteristics. Now the importance of this one is here is that when you are starting the motor is not rotating, there is no back EMF, so there is usually the initial inrush of current. So we want an overload device that will take care of that, to not trip the minute the current is exceeded. And mostly for this ones here, we have the bimetal strips, because they need to heat up before they operate, or connect a switch to switch off the supply. In case it was magnetic, when you're starting the motor, the current is usually high, sometimes 3 or 4 times the normal current, they would trip. But the time lag characteristics, it means they will take time before they trip. That would mean the motor will start rotating, produce the back EMF to control the current that is flowing in the circuit. And of course the time lag, you can set the time, between which time before they trip. So that's a recommendation, one of the recommendations of the IEE. And the other general one is that motors rated less than 370 watts. Now in the old units, this will be a half horsepower. In the earlier times, horses what used to be the power source used to be measured in horsepower, half a horsepower, need no further device. No further, sorry for this one here, no further protective devices apart from the overload tripping device. So now in our circuit connections, we are going to deal with more of these IE recommendations for the motor connections circuits, which means every motor shall be provided with, of course, this one here is excluding the one rated less than 370 watts. Number one means to prevent automatic restarting after a stoppage due to power failure or drop in voltage. In industry, when you're connecting motors, one of the things we check is the voltage. Voltage drops at a particular level, then there should be a mechanism for stopping the motors. So when this happens, or there's a power failure, the motor should not automatically restart. However, this provision can be overlooked in certain conditions. However, this provision this provision can be omitted. As when the motor is automatically controlled, or if it would be dangerous if failed to start after a temporary interruption of the supply. So that is a key recommendation of IE, means to preventing automatic restarting, and these are the two exemptions. If automatically controlled, or if it would be dangerous for the motor to not to restart when the power comes back. Of course, this second bit, fail to start, dangerous. If the motor failed to start, maybe in hospital theaters, whereby power supplies is required. Any motors connected there, maybe pumping the oxygen and the like. This bit of preventing restarting is done away with, so that the power comes back, the system can be restarted again. And then, number 2 is where more than one method motor. The more than a method of starting the motor is provided, then means must be provided to prevent restarting until every stopping device has been reset. And then the third one, an isolator must be provided. Oops. To cut off all voltage from the motor and its control gear. And if the isolator is remote from the motor, then an additional isolator must be provided. Number 4 in every place. Where machines are being driven by motors. There shall be means switching off the motor or stopping the machines. If necessary, to prevent danger. The means at hand could be the isolator, starter, stop buttons, or clutches on the machines. Usually, if the machine is driven by a motor, there will be a clutch between the motor and the machine. And the other requirement which we need to know is that if there are various stop buttons provided for stopping the motor, depending on the setup. That means the fifth one, it is desirable to provide in various parts of a factory so that the whole or part of the machinery can be stopped in case of emergency. And these stop push buttons So in the case of AC motors, the stop push buttons are meant to open the hold-on coil circuit of your starter or circuit breaker in the case of AC systems. And in the case of DC motors, is to short So those two different methods of stopping the motors. In the case of the AC systems, we open the hold-on coil, and in the case of DC systems, we short the hold-on coil. A major difference between the two. So in the circuits we are going to control for the motors, all these 5 things, they should be desirable in the circuits that we connect. So now we are going to see the actual circuits of the connections of the motors. Now to connect the motors, in order to embrace all those 5 conditions, we have starters. Now in most drawings, the power we saw it when it left the bus bar chamber, it went to an installations, and in that installation, there will be a series of maybe series of circuit breakers or fuses. I'll explain as we go on. So now, in the shop floor, there will be a kind of a distribution board, and then there are several motors. Now we have said each motor must have its own isolator, which is that one there. And then you find in the drawings, normally, we can use a single line, like that one there, to show our connections to our motor. Now, this is a single line diagram, but what we know is that in here, there are 4 conductors. That will be, now in this case, this is a 3-phase motor. 3-phase motor, there is the live which comprises of the red, yellow, blue, and there's also the neutral. So this will be 4 of them, or they can be 3, depending on the motor connections. So they can be done something like that. It means there's a wire from here. If this is our neutral connections, this may be the circuit breakers for the, this is red, Y, and B phases. The circuit breaker from the B phase, yellow phase, red phase, and then they all come together, 3 of them, and then they come to the isolator. So this will be isolator. Again, you have to learn the symbols. This one I've given free for you, and this one here is our starter. Now this starter here has to fulfill the conditions we have talked about, and this here is our connection of the motor. Now the starters, there are various types depending on the motor. Now that one is the general symbol for the starter. Then we have got various types of starters, and I'll give you some of the symbols of the starters that we shall be using. Now, apart from the general symbol, we have got what we refer to as the DOL. Direct online starter. Now, there are those small motors which you can connect directly onto the three phases without much complications. So this kind of a starter, the wiring will be different from the other types. Then we have got another type of starter which we can connect to do the forward and the reverse. So this is DOL, forward and reverse. Starter. Now these are motors you connect direct on the line. Normally the KPLC, or if you have done you have got your Class A license in electrical installations, you'll be knowing which motors you can connect like this. But the PLC, when you come for them to connect power to the installations, normally if you're doing motors, they'll ask you what kind of motors you have. And then when you come to there are those motors which you cannot connect them DOL, usually the large motors. And for those large motors, we have got what we call the star, delta, starters. Now, this means when you're starting the motor, you first of all connect it on star. In your circuit analysis, you analyze the currents. When the motor, the stator windings are connected in star, what are the currents involved? When it's connected in delta, what are the currents involved? In star, the currents are less, so you start the motor in star, and then you change over to the delta. And then we have got auto transformer. You can also use an auto transformer. But of course, all this goes for the large motors. Then again, for the large motors, we have got some motors which operate in steps rather. And basically, those are the ones that will be coming across. Of course, there are other types depending on your motor connections. Now, these again are symbols, part of the symbols that we talked about, the exercise that you have to do, motor connection circuits. All these symbols, again, they are symbols whereby the next examination you can be asked to reproduce. So, briefly, let's have a look at one of those starters, which I'll call the DOL. Now, if you were to draw a schematic diagram for that one, the DOL, what it means, this is the schematic. I'll be having the isolator, which you said is a mass for the motors. And then I have the symbol for the direct online. In this case, it's just moving in one direction. And then I have my three-phase motor here. In this case, I want a cage, rotor, induction motor. I think in your circuit analysis, the three-phase, the cage rotor induction motor you are aware of. In that others, the rotor, they are just copper bars shorted at each end. The only windings we have are for the stator windings. So a schematic diagram would look like that one here. So this one here is a isolator. Remember the 5 conditions we talked about? This one here is our DOL starter. And this one here is our motor 3-phase. Okay. Now, before we proceed on to connect these circuits here, let's briefly discuss about the motor. Now, the motor as a block will be having a terminal block. In the terminal block, there will be 6 terminals like that one. Let's assume this whole thing is your motor. This one here is your motor terminals. In this case is the cage rotor. That means this will be the terminations of your windings. Now, in the case of the motors, in the BS system, you find that the winding, these are the stator windings, one of the windings will be starting from that terminal there, go inside, it is wound, and then come out, the other end is terminated here. The starting, the end. And then for the second winding, it starts there and is terminated at that point there. And for the third winding, it starts there and is terminated at that point there. Like that. Now, when you come to any motor, it's good you establish the connections. Because like when it comes to the star-delta connections, you need to know how these terminals are connected for you to be able to connect the motor. Now, to establish this ones here, you can use simply an ohmmeter. And simply place one probe here and the other one on the other terminals. Then you can draw this pattern so that you know how the windings are connected. Now, from this ones here, you can see that if I want to connect the stator windings in star connection, now a star connection is usually something like that. Like that. The winding is like that. So this is the star point. This is one end, the other terminal, like that. And then these are my 3 phases, L1, L2, and L3. Now you can see in my star, the end of the windings, I've connected them together, and the beginnings are the ones which I'm connecting to my power supplies, or rather towards the starter. So if I want a star connections of these ones here, I can simply short the lower terminals. This one's physically on the terminals, you put a piece of wire like that, and then your power cables, 3-phase cables will come like that one, going to the starter. So that connection will be star connection, which will be that one here. The endpoints are the ones which I've connected together, and the other ends are the ones which I've connected to the power. Now this is for the star. Now if I want to connect them in delta, the story will be slightly different. All right. Now, for a delta connection, it will be something like that. That would mean the end of one coil is connected to the beginning of the other one. So this is the beginning of one coil, this is the other end. This is the beginning, the end, the beginning, the end. So the end of this coil here is connected to the beginning of that one here. The end of this coil here is connected to the beginning of this one here. And the end of this one here is connected to the beginning of that one. Now to achieve that kind of connections with this kind of a motor, if the windings are connected like that, it means I short the top here to the bottom. That means the beginning of this coil here is connected to the end of that one there. And then here, I short this one here. The beginning of this coil here is connected to the end of that one here. And I short this one here. The beginning of this one here is connected to the end of that one there. And that connection then proceeds on like that. So this is for the delta connection. So before you connect any motors, you need to establish how the windings are. I think the Chinese connections of this one here is slightly different. They start from the top to the bottom, top to the bottom, top to the bottom. So you can establish this one here simply using an ohmmeter or a low resistance meter to know how they are connected, and then you can play around with them. So in the case of my motor here, I can connect it in star connections if it goes DOL. Remember, we said in star connections, the currents are less. So now that is the schematic. Now here, I can produce the wiring diagram. Now much of your NEC examinations, they will be looking for the wiring diagrams. So in this case here, I've got the isolator. In the isolator, I need to isolate the three phases. Then from the isolator, I come to contactor, the one which will be doing the switching. Now the contactor will be having terminals like that one. And then from here, I will need a time lag overload device. This one here will come to the motor terminals. And then this one here, I'll short that one there to get me my star point. And this one's here, my motor terminals. This one here is my thermal overload. This one's contactor contacts. And then I'll have the usual fuses for the overload. These three are linked together. Well, 1, 2, 3. Now these connections here is usually referred to as the power circuits. In these ones here, there are heavy currents. There will be heavy currents flowing in these circuits here. Now for the thermal overload, there is a setting trip. You can set at what current you want it to trip, depending on the size of your motor. Now the contactor circuits, again, the contactors contacts, there is a particular amount of current they can carry. So depending on the motor, you go for a particular set of contacts. The main fuses, they've got a bearing on the motor connections here. And this isolator here is simply to cut off the power. Remember the 5 IE conditions we talked about. And then I've got the control circuits. In the control circuits, we normally have what we call the overload tripping device. Now this one's here, this contact here will be operated by this thermal overload. When it trips, it will open this circuit here. Now usually this one is just a minute. There are usually two contacts like that. So this one will be, one will open, one will be, this one will be closed, and this one is usually looped like that one. So the overload, in case of tripping, this is overload, tripping contact operated by these ones here. When they sense an excess current, the mechanism will open that contact there. Then we said there must be facility for stopping or starting our motor. So we have a stop push button. And then I have my start push button. And with the start, this one is spring loaded. Once I release it, there will be the hold-on contact we talked about, which we said will be opening the hold-on contact when we want to stop the motor. Now, the additional contact, these ones are usually, this contactor here has got 4 contacts. When you buy them in the market, they can have 4 contacts in which all of them will be normally open, or they can have 6 contacts. The 5 will be normally open, and 1 will be normally closed. They are available in the market. In case you want more contacts, you should be doing the other circuits. There are some circuits where we'll be needing more contacts on the contactor. So let's assume we are moving this one of 4. So they'll be like that. All these 4, they move together. When the contactor is operated, they move like that. This one closes, all this closes, and we've got the push button there. Then from the push button, I simply go to my contactor coil. Of course, this one goes back to the neutral. So this is overload. This one is stop. Push button. This one is start. Push button. This one here is the contactor coil. Now the drawing is normally drawn like this one to avoid the confusion. Now this coil here operates these contacts here. In other words, they are like one unit. Maybe I can expand it slightly bit here. I can expand its operation is something like this one here. Now this coil here, this is the coil, and these are the contacts. So when this one is energized, it will pull the plunger inside. This one is insulated, so that does not short the contacts. And this end here, this one is magnetic, so that the coil can interact with this one here. When it's energized, this one pushed in, and these contacts here make. I think it's by coincidence that this contact here has aligned itself with this other 4 here. In some drawings, you might find this one is separate. But then we normally name these contacts so that you know which belongs to which one. Maybe if I call this one K, contactor K, then this will be contact number, maybe K1, K2, K3, and this one will be K4. So each contact should be numbered so that you know which contactor it belongs to. In this case, there's only one contactor, so maybe that bit does not arise. And then this one referred to here as the control circuit. And of course, all circuits must have a fuse protection. Now this overload contact here, when things are normal, running normally, this circuit here will be completed. When there is an overload, this one here will trip. And when it trips, these other contacts here, this one will come and, usually there are two different sets of contacts. This one connected. This one will come and connect to that side there. And then here we have an indicator connecting like that one here. This will be a trip indicator. Trip indicator. In case it trips, this mechanism here will move into the other direction to open this contact here, close that one there. When this one is closed, there will be a path for the feed to give an indication that this particular overload has tripped. And that is our control coil. Now, all these components, the contactors, I think I'll show one next time we come in. The stop push buttons, so the start push buttons, and the contactor, I think I can show them to you in our next video. So briefly, that will be the circuit of a DOL. Now, how does it operate? Now, before we look at the operations, let's talk about the contactor. Now, the contactor I'm using here is connected. You can see it's from L1. The circuit goes all the way back to the neutral. So this contactor here is operating on 240 volts. Now, in the market, you may get contactors which are operated by rated 415 volts, which means if this one is 415 volts, then these other connections here will have to go back to either L2 or L3 so that this one gets 415. So there are different kinds of contactors available in the market. You as the designer for the circuit, you are the one to decide which one to use. Now, another thing I found out in the market is that most of these circuits from China, instead of using either 240 or 415, they change these ones to DC circuits. So you find that this one is operating on 12 volts. Maybe so the circuit will be slightly modified, slightly different. So this one is 12 volts. This one is the usual power rating. So it's for the designer to decide how to connect the circuits, but the principles more or less remain the same. So that's the principle of operation of a DOL. The sister windings, you connect them in star, and the motor is a cage rotor. There are no rotor windings. So when you want to start your motor, you operate your isolator to close your circuits. So this one connects there, this one to that point, this one here to that point there. And then you can see that when you move it there, the power will be available up to the top contacts of your contactor. The power will be available up to that point there. And then on the control circuits, the power will flow through the fuse. Overload, this one is making the stop push button not pushed, that one is making, and come to the starter on the top side of the contacts. Now, the next thing is when you want to start it, you press your start push button. When you press that button, now the power is available from here. Now it can flow all the way around through the start push button. Our coil is energized back to the neutral. When this contact here is energized, these contacts here will move to the left. They will close that contact there, this one here, this one's here, and the power flows to the motor, and your motor starts running. And of course, you can see when this one's closed, this one will also close. And usually this terminal, this contact here, is referred to as a hold-on contact, in that when this one operates, this contact here will make. So that for this coil here, there will be two paths available. The one through the start push button, and the one available through the hold-on contact. Now this start push button is spring-loaded. Once you press it, you release it to spring back to the open positions. The way I've drawn the circuit is how the contacts are when there is no power connected to the circuit. So this one is spring-loaded. So when you push it, this contactor energizes. This contact here, when it makes, means there are two paths available, such that when you release your push button, this one will open, but this one will be kept energized through this contact here, which you call the hold-on contact. And remember, in the 4 conditions we said, if there is an emergency, we need to interfere with the hold-on coil circuit. And that's when you press your stop push button. When you press this stop push button here, the power will cease to flow into this one here, and this one here will open. So once you start, this one becomes the hold-on contact, and your motor continues to run until the time you want to stop. When you want to stop, you simply press the stop push button and you interfere with the hold-on contact. So this one's de-energized, this one breaks. Again, this one is spring-loaded. When you press it, it will open the circuit, and then when you release it, to come back to that position. But then when it comes back, you'll find that the motor cannot restart because this cannot be energized. There is no path for it, fulfilling one of the IE conditions that the motor should not automatically restart until you start again with a push button. Let's assume you have pushed it on, you have started it, it's running, and then there is a power failure. When there is a power failure, again, this one will be de-energized. Once it's de-energized, that contact will open. Then maybe the power comes back. When it comes power back, this one cannot energize because that one is open, it cannot restart. But I think with that one we have fulfilled all the 5 conditions that I talked about. Now, on the other hand, if your motor is running and then for some reason there is an overload on the motor, maybe the motor is obstructed and then more current starts flowing in, your thermal overload will trip. Once it trips, it will open this contact here. As you can see, this contact here is in the path of the holding on of a contactor coil, and then this other contact here it moves on to the other side. This contact here will make, and your trip indicator will come on. So the motor will switch off, and your indicator for the trip indicator will come on. Somebody can know that your motor has tripped. Briefly, that's how our DOL operates. Now, as I said earlier, when you go to the industry, there are more additionals to this circuit. For a start, we detect in case there is a failure in one of the phases in industry. If there is a failure, there should be an additional contact to switch off our motor. The other one is, in case there is a lower voltage, it needs to be detected and the feed to your motor should be cut off. The windings of the motor can also heat up. Again, you detect the heat on the windings, and again, that sensor is connected to your control circuit to stop your motor. And that's all there is to the direct online starter. Now, you should be able to recall this circuit. Come examination time, you can be asked to draw this circuit here, and at the same time, you should be able to practically connect this circuit. So I'll be showing you the components, and then we shall also carry out a practical connection of those components for you to have an idea of what the whole thing is all about. Before I go to the practicals, I'll show you the components, what they are, the contactor, stop push button, the overload, those ones which are available. I can show them to you so that you are able to move together. And of course, this particular design is my design. Other books, they might have different designs, but the principle of operation is the same. Of course, as usual, any questions? Oof. Now we are finished with our direct on line, which was moving in one direction. Now we come to the circuit of direct on line with forward and reverse. So our motor can move, we can move in forward direction, and also we can move over to the reverse direction depending on how you operate it. Now with this kind of a setup, we need to ensure that in case the motor is running in the forward direction, we cannot connect it to move in the reverse direction. So here I've included some two contacts which I'm usually calling to the interlocks. That means if the motor is running in the forward direction, then if you try to operate the reverse, there will be no feed that will be available. Then the other thing we need to note is that now I'm using more contacts than the usual 4. If you look at the forward contactor, which I've labeled F, now any contact pertaining to the forward contactor has got a label F. So F here, there are these 3 here. There's also this other one here, 3, 4, and this other one here, making 5. Now this one and these 3, they are normally open. This one here is normally closed. That means in this case here, I'll need my usual 4 contacts and another contact which is normally closed, a normally closed contact. So for this one here, I can go for the contactor with the 6 terminals, of which I said 5 will be normally open plus 1 normally closed. I can go for that contactor. The alternative is I can go for what we call auxiliary contacts. These auxiliary contacts are usually mounted on top of these ones here. Again, I'll show you what an auxiliary contact looks like. And they usually come in 2s. The 2 you have to make this one here, the pair you mount on top will be having one contact normally open and the other one normally closed. So here I will need auxiliary contacts for these circuits here, or I go for another type of contactor with that kind of an arrangement. And of course, my contactor coils here, they operate on 240. As you can see, it's from live to the neutral. Now, again, when I want to open the circuit, to start the circuit maybe in the forward direction, then I close my isolator. Once the isolator is connected, again, the power will be available up to the top terminals, and in this case, in both in the forward and in the reverse. Now, depending on the push button you push, is the one that we connect to our motor. So let's assume I want to move it to move in the forward direction. So I'll press my forward push button here. I think it's visible. F. When I press this one here, the story is similar to what we had in the DOL. So when this one is pressed, these contacts here will make the feed is available to my motor. And also when I press this one here, the feed is available to this contactor here, which will close. Of course, when this one closes, it's when these ones will close. This one will close. When I release my push button, then this one becomes my hold-on contact. Now, in the way I've drawn, I told you that these contacts here, we normally draw them when the circuit is de-energized. So you can see then that when this one operates, these contacts here will close, 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 but this one here will open. In this case here, these are moving in that direction here. So maybe this one here, we can draw it onto that side there. Now this forward contact is in the reverse control circuit. So when my contactor is energized, this will close, this three will close here, but this one here will open. When this one is open, in case you press this push button here, as you saw, the power is available up to here, all the way up to here, and here, and here, and here. So if you press this one, when this one is running, then this contact here will be open, so your feed will only come up to that point here. This one cannot be energized. That's why they are called interlocks. They interlock each other. When this F is in operation, this contact here opens, you can get a feed to this one here. So your motor runs in the forward direction. And then, once in the forward direction, I've included an indicator here. Now sometimes in a shop floor, there may be a lot of motors running, and you want to, maybe the supervisor wants to know in which direction it's running, or even the operator, when the motor is running, you need to know which direction it's rotating. So you connect an indicator here for that contactor, indicator here for that contactor here. So when this one is energized, these lights will come on, indicating the motor is running in the forward direction. And then, when I want to stop, I simply press my stop push button. When this one is pressed here, the feed to this one here is interrupted. And when this one becomes de-energized, these ones will now move to that open position. This one move the open position. When I release my stop push button, this button will come back. Again, the power will be available up to that point there, but cannot go beyond because neither of the push buttons is operated. So the motor stops. I think everything is clear. Then, after stopping the motor, maybe I want to run it in the reverse direction. Now, with AC motors, when you want to reverse direction, you simply reverse any two of the phases. Now, what the R contactor is doing here is simply reversing the connections of L2 and L3. As you can see from my diagram here, the L1 on top, F1 will be connected to the bottom. The same with R. When R2 is connected, L1 will be the same. But with the L2, whereas in the forward direction, the L2 is connected to the middle terminal here. When it will be in the reverse, this middle terminal here will be connecting to the third terminal, and the third terminal will be connecting to the first one. So in the forward and reverse, I've interchanged L2 and L3. Remember the write-up of the motors. Well, if we have something like that, if this is 1, 2, 3. If I want to reverse that sequence, I simply interchange any two. If I interchange this one here with this one here, it will be 1, 2, 3. If I interchange this one with this one here, it will be 1, 2, 3. So interchanging any two will make sure that the rotation for a motor is changed. So again, in the reverse, I press my reverse push button. This feed is available. I have not pressed my F contactor is not operating. That contactor now that is available. This contactor back to the neutral. This contactor is energized. Once this one is energized, these three here will close, and this one here will close, and this one here, I think I've drawn it in the other hand for correspondence sake, this one being like that one. When these ones move, this one will move, and this one will open. Now when this one is open, in case you press your F button, the feed cannot come to the F. So the interlock name for these two contacts. So when this one is making, you raise your reverse push button, your feed now is available through this contact here, which now becomes the hold-on contact for the reverse, and your contactor is energized, and your motor continues running in the reverse direction. That means your L2 will come to this point here, move across here, come and join this one here, becoming the position of the former L3. And for the L2 coming up here, the L2 coming up here will join the position of L3. And for the L3 coming up here, it moves to the position of L2. So the L2 and L3 are interchanged for the reverse. Your motor runs in the reverse. Then when you want to stop, you simply press the stop push button. Now in this circuit here, I've shared the stop push button. The stop push button is common to both in the forward direction as also in the reverse direction. In some other circuits, you might find that there is a stop for this circuit here, a stop for this ones here. The interlock will take care of that. One cannot work at the same time. And I think that is our forward and reverse. Remember, our stator windings are connected in star. That's why I've shorted that point there to get my star points. The currents will be less. So the installation for the workshop will dictate the size of the motor up to what maximum can be connected directly on line. So for the bigger motors, there are methods of starting them, which is the direct on line, the star delta connection, the auto transformer, and other methods which we'll go through in the following lessons. In case of any queries, you can send them in. Now, as I said, this circuit can be different from the one you draw or see in other books, but the principles remain the same. Only in industry, there'll be some slight changes in that they have to ensure the motor is stopped before you move from the forward to the reverse, the voltage checking and the like. But that basics is the basics for the direct line, forward and reverse. There may be other additionals, but the basics is okay. Come examination time, what I've done here is sketching. Your diagrams for the straight lines, use your instruments. Use a compass so that the whole thing is neat. But at our level, we are supposed to be using the AutoCAD. We do all this stuff in the computer. Of course, once you get the basics, transferring onto the AutoCAD can be easier. So our next circuit will be star delta, which again will do the schematic as well as the power circuit, power and the control circuit. Again, control circuit, less currents flowing. Power circuit, where you have got the heavy currents. Thumb overload, you can set at what current you want it to trip. And as I said, the contactors, you can decide whether they operate on 240 or 415. With 415, I said the connection will be slightly different. You connect this one to another phase, and you connect a control fuse. And that is our schematic.